Welcome to Data Science with AJD. I know you've been itching to see codes. Finally, we're at that point where we get to see codes and see some of the things that we've talked about theoretically practicalized. And in this video, we'll be looking at linear regression, which is a supervised learning method in machine learning. So linear regression, we'll look at it from scratch and scikit-learn also. Okay, so is our introduction. Linear regression. What is linear regression, right? Linear regression it's one of the most popular machine learning algorithms out there, right? So linear regression is a supervised machine learning algorithm used to model the relationship between input features and a continuous target variable y by fitting a straight line or hyperplane through the data. Now, simple thing. If you are looking at growth, right? What are the factors that contribute to the growth of a child or the growth of a person or the growth of a plant or something? So you may want to look at genetics, you may want to look at the environment, you may want to look at nutrition. So in this case, your target would be the growth maybe as measured by height or weight or whatever. And on the other hand, you have the input features like genetics, nutrition, and environment, possibly. So, and if you find a way of measuring all of that, then that's a very nice example of what linear regression looks like. But since we said it's a supervised learning kind of thing, I tried to explain it in a previous video, but actually, I'm bringing it up again for clearer understanding. Supervised learning is simply a type of machine learning where a model is trained on labeled data to predict outcomes for new unseen inputs. Now, here we are saying supervised learning has something to do with labeled data. Now, that's another idea. What is labeled data? Labeled data is simply a data set where each input is paired with the correct output or target value used for training supervised learning models. Maybe that is still sounding like gibberish, right? We can go on and talk about that. Labeled data is like a collection of emails. So if you have a collection of emails where each email is marked as either spam or not spam, to help train a spam filter. That is what a labeled data is. So you have data for different for maybe for 500 students, and then you can categorize some as male and female, or some are in first year, second year, third year, and things like that. Those are labeled data. Now, when we get to unsupervised learning, you'll understand why we have to talk about labeled data and unlabeled data. So, but here we are focusing on labeled data. So let's go ahead and talk about the linear regression equation. So this is what that looks like. So you have this y cap because beta naught plus beta 1 x1 plus beta 2 x2 plus all that beta n xn. Now, if you look at my statistics playlist, I think there was a point where we got to fit we do this kind of linear fitting, there. So you want to revisit that to refresh your mind, to rethink it, or I can also make it come right after this video. So you want to watch out for that. By the way, don't forget I have this code sheet. You can, before you even start watching, following the video, you can download all the slides and code sheets from the link that will be provided in the description box, so you can have access, so you can download this and follow step by step. Okay, so looking at linear regression equation, now you have y cap is your predicted value. So if you predict a value, xi are the input features like all this x1, x2 up to xn, depending on the number. So if I use the growth case now, so maybe after fitting, you now have your predicted value to be the predicted value of growth to be something in particular, and the input features like say genetics, nutrition, and environmental factor or something like that. Then you have the intercept. B naught is the intercept. The intercept is simply a base value. It's like your baseline. So whatever you have when every other thing is zero. All right, that's your intercept, and then beta one are the coefficients. So those are like the slopes, right? They are the multiplying factor for those features, those input features you may have. So they determine how fast the model grows. So this model aims to minimize the error between actual and predicted values by minimizing a loss function. So you see, this is your predicted value here. So the actual value is probably what you have from a data set, right? So by the time you find the difference between each thing you have in the data set and the predicted value, then you can square that and sum it up and divide by n, and that gives you the mean squared error. And this is the formula you have right here. This is the mean squared error. So this is the linear regression equation itself, and then this is the mean square error, which tries to minimize the difference between actual value and predicted value, and then you want to minimize the loss function. And then that takes us to linear regression, and we want to see the math behind the model itself, right? So we have a normal equation, or what you can call a closed form solution. So we can directly compute optimal weights using theta, which is x transpose x, all of that inverse multiplied by x transpose y. So where x is actually the feature matrix with a column of ones for the intercept, right? And y are we talk about is that will be the target values, right? So this x now, it's not just, it's a matrix for sure. So if you have three values, so it means you are going, so you have the intercept, and then you have all those three values, right? Then you have theta to be the vector of coefficients including intercepts. So this method avoids iterative optimization, but it can be inefficient for large data sets. So if you have large data sets, this may not be the best thing to use. So as we go on, you might stumble on things like that. So our use case here is want to predict diabetes disease progression using the diabetes data set from scikit-learn. So in machine learning, I'm going to be using most of the data set that are available already on scikit-learn. And you are going to come across some of the data sets we've seen before, like the Titanic data set and all of that, right? Then we also have the diabetes data set. Okay, yeah. Since we are talking about diabetes, so let's explore the diabetes data set. The diabetes data set is included in scikit-learn. It consists of 442 samples with 10 features each, and they are standardized real-world clinical data. So they have features like age, sex, body mass index, average blood pressure, six serum measurements, right? But of course, they have been anonymized so that, of course, nobody's information is revealed. And it's a standard data set that is used a lot for these things. So in this case, we now want to focus on a target. So we need a target, and then we need the input features, right? So here we have a quantitative measure of disease progression 1 year after baseline, right? So here now, so we have to import the diabetes data set, and that's, so the approach here is we just say sklearn.dataset. So we have the dataset module in scikit-learn, and from there you have all the possible data sets. So you can load diabetes, all right, the data set, and then now you have the diabetes. I think it's always good to have line number so I can easily refer, right? So you load diabetes, and in line 3 you have a, for it's just a diabetes as a variable name equals load diabetes, and then if you print that, it gives a data set fit for the kind of thing you want to do here. So if you run this now, so it gives us an array of data like this. So we have all those possibilities. So you have all this, it doesn't look so friendly like what we have been used to. So, but you see baseline variables, age, sex, body mass, you have all of that going on there. So here now, so if the X, which is the diabetes data, so you can get your X value from there. So you just extract that out. So just the diabetes.data. Um, so let's see, where did you have data? Yeah, so this data itself, right? So this has already been standardized for this job, right? So the data are the input variables, while the target is just only that one target, which we said it's a quantitative measure of disease progression 1 year after baseline, right? So all of that has been separated for us. So we can just say, so from the so it's more like we have that. So all the input data have been put together, and the dimension is 442 by 10, right? So we just say x diabetes is equal to diabetes data. So, and I put the x in line 2 to visualize it. So you can see it has given us only the x, right? Like that. So it gives us the top five and the last five as usual. Then we have the same for diabetes to targets, which gives us the target value. So we want to do a regression between this target and the data, right? And see how that goes. So now we are using to approach, in this case, we are looking at linear regression from scratch. Like this helps us to go step by step. But then we can also use scikit-learn later, which is more, which goes more straight to the point. Like in fewer steps, you get your results. But if you do from scratch, you can understand the step by step procedure of that. Okay, so linear regression from scratch now. So you see in step one, we do the setup. So in the setup, you want to import numpy as NP as usual. Then from scikit-learn, the model selection, you want to import train test split because we need a train data, and we need test data for sure. Then sklearn metrics, you need to we are importing mean squared error and R2 score, right? Of course, once you have mean squared error, you can easily get root mean square error by just taking the square root of that. And SKRT can come from NumPy. That's why we need this NumPy here. Then that's step one. You set up, you import the necessary library. Don't forget to run so that it can be registered. So all of that have been mounted. And then we go to step two where you split data. So as usual, you have X train, X test, Y train, Y test. So these are the two things. You have X train, X test, Y train, Y test. And then you now call the train test split function. All right. And then you throw in the X and the Y, and the test size is 0.2. That means you're using 80% to 80% of your data to train, and you're using 0.2%, 20% rather, to test. And then random state is to make sure that even if you run it several times, you keep getting the same result. Because if you don't do that, so you can get randomized results, and it will be difficult to measure against a particular baseline. So it's better to just have it static this way. So by running that, we have that settled. So the next thing we want to do is we want to define the model class, right? So here, so we are doing some kind of object-oriented programming. So you define a class which you call linear regression from scratch, linear regression scratch. So, and under that you have some functions. So you want to fit self x comma y, xb. So from numpy now you have ones for the, you're adding a bias term now. Then self theta now. You remember that theta we saw up there? That theta that was you know get together with some matrix kind of thing. Yeah, this now. X transpose X inverse X T Y. So that's some approach. So that's why doing from scratch gives you some mathematical feeling to what is happening here. So you have linear algebra inverse of XB t dot xb dot xb. So this is just a translation into mathematics or into Python of that theta expression you have up there. Then you also, so this is fit now. Then you now predict self x now, xb again. You now have the ones and all that, and then you return xb dot self theta like this. So again, that's the model class. So I run this and it's done, no errors. Then we for step four, we train and predict, right? So model scratch. So you have linear regression from scratch. This linear regression from scratch that you've defined in this line one here, starting from that. So you are bringing that up here. Then now model scratch dot fit. So X train, X, Y train. If you remember in the last video where I was just talking theory, like showing you a slide. So this is the kind of thing. So it's the same procedure we are having here. So in this case now, so the first two lines is where so here, this is where you call the kind of model you want to use. In line two is where you fit your data to that model, your train data to that model, and then line three is where you predict. So you now have model scratch or predict S test. So if you run this now, so this X test now you're throwing it into the model to see the value of what it gives you. Now we have run that and we are good. So the next thing now you want to evaluate that. This is us doing it from the scratch. But if you're using scikit-learn, we don't need to go through all that stuff. But doing it from the scratch gives you a feel of what is really happening in the background. So MSC, that's mean squared error from the method you have applied it as. So you get mean squared error, which is a function from that you have imported already. So on the Y test and Y predict. So you want to, so this helps you to see, oh, the test value you used initially, and this is the predicted value you just got here. What's the difference? Then R2 from scratch to gives you the R2 score between the two. And then if you run this, we get that. So we see the mean squared error is 2900.19 and the R squared is 0.45. That looks a bit okay, but I mean, most of the times you want an R squared score, which is very close to say one as much as possible. So this can be, but I mean, so this can now lead you to, if you are not satisfied with this, you now want to go for some hyper parameter tuning to make things better. But we'll get to talk about that in subsequent videos. So now that is us doing it from the scratch, and doing it from the scratch actually helps you to understand the step-by-step thing, just like the one presented in the slide in the last video. So now let's go on and talk about linear regression using scikit-learn. Scikit-learn is uh, that Python library That is, once you're scikit-learn, you're talking machine learning basically, and then later we move on to things like TensorFlow and say PyTorch. I mean, there you're good to deep learning and all the rest. We'll probably get to those ones too. So here you have, so previously we had 5 steps. Here you have just 2 steps. You understand? Like it's just more straight to the point. So if you have mastered the process, then this is where this works. So from sklearn.linear model, you can import linear regression. So you have model sklearn is, so the model you're using is linear regression as usual. Model sklearn, you are fitting the train and the X train and the Y train. Then you are predicting straight up. So model sklearn predict X test. So it's like everything you've done previously in one blow. So you have that here. Then the next thing you're just doing the evaluation straight up. So the MSE and R2 for sklearn. And then if you do this, you get exactly the same result like before. So it's giving you the same results, except that here now we did everything step by step. So, but I mean, in a setting where you get to do this every time, scikit-learn just works for you. So if you now want to do a visual comparison, right? So you want to use matplotlib, and then here you want to see you want to have a scatter plot of the y-test, y-predict from scratch, y-test, and y-predict from sklearn also. So you have color blue, color green. I guess blue and green look so much alike. Maybe I should make this red. Let's make this red to really distinguish. So we have alpha, so label scratch, then scikit-learn. Then you also want to plot minimum, maximum, and all that for all of the other values. So if you run this now, you have see what you have right here. So like the scikit-learn stuff, it I think it looks like everything is coinciding, right? They're all coinciding, so you don't really see the difference like that. So everything is coinciding. Then you just have this line going through. That's the line of best fit, so to speak. So that's your line of regression, right? So we have that going on there. Okay, so in summary, right, the model summary, you see the MSE is between 2900 to 3300 for both. Then the R2 scores are about the same, 0.45. The intercepts for from scratch, the intercept is manual, but from scikit-learn it is automatic. Then the coefficient estimation, so from scratch it's normal equation. For scikit-learn it is optimized solver. And the real world use case from scratch, you can use it for educational purpose. And for scikit-learn it's for production, like when you have a whole lot of data, right? So I mean, from scratch is good for maybe just teaching, like this kind of teaching I'm doing right now. But if you want to use it in a normal industrial environment, scikit-learn is the go-to library, the go-to thing you should do. So key insights so far. So from scratch teaches core mathematical underpinnings and enhances intuition. Then scikit-learn handles edge cases like numeric, and it has numerical stability and performance is more robust. So the diabetes data set is suitable for demonstrating multi-feature linear regression and evaluating model performance realistically. So if you look at the diabetes feature, right? So we have the target Y. The target Y is this is just this one thing, whereas the array, the diabetes, the X data, you have an array of say one, two, three, in fact, a lot. I mean, you have 10 things, right? You have 10 things, 10 stuff contributing to Y alone. Okay. So that's what the diabetes data is doing for you. In final thoughts now, start with Scratch implementation to grasp the maths, then use libraries like scikit-learn for fast, efficient, and scalable deployment. Okay. In the next videos, interestingly, I'll be talking about how to deploy machine learning models. Though I may not be able to implement it fully because it involves other things like cloud. You may need to talk about cloud computing. You may need to talk about things like Docker or Docker, which I'm not interested in at this point in time. But I'll just give a kind of general overview of what that looks like. Then you also want to combine both to become a better machine learning engineer or data scientist. So let me know in the comment section how helpful this video has been for you. If you have subscribed already, please go ahead and also hit the notification bell so you can always get alerted each time a new video is released. If you have not subscribed, of course, go ahead and subscribe and also hit the notification bell. Of course, you can become a member of my channel. then you can, of course, follow this playlist so you don't miss out on anything. Be sure to like and share so that more people can have access to the great content that I have going on here. Till I come your way again, keep doing data right. Bye.